everybody, and welcome to our IBM-Z security ecosystem series, Secure System with our ecosystem. A warm welcome to today's story, and our topic will be passwords. So mainframe passwords revisited, impact of new security mechanisms, and I'm very happy to have our friends from Detack with me. So together with me on stage is Costin and Octav from Detack. My name is Patrick Kempeler from IBM. I'm the zStack platform lead. And yeah, welcome Costin on stage. I would like to hand over to you directly. And yeah, maybe you can give us a short introduction of you and your colleague and what Detack is doing at all.
Okay, thanks, Patrick. Yeah, so I'm Costin Enache. I'm managing director at Detack. I'm a security researcher, consultant, occasional developer with a keen interest in mainframes, and one of the authors of our EPAS solution, which is a solution which addresses the password problem on mainframes. That means detecting predictable passwords and preventing their use, or leaked passwords and their use. I'm joined by Octav, who is also a mainframe security specialist. He's been doing mainframe security for quite a number of years as a pen tester, consultant, and also developer of mainframe security solution. He's also one of the authors of our EPAS solution that we are going to use throughout the presentation today to give you some examples of what can go well or wrong with mainframe passwords.
Very nice to meet you. Thank you. And hello, everybody.
Okay. Good. So why do we want to talk about passwords? Well, mainframe passwords are one thing, but passwords in general are the most widely used authentication system today. We are being told that passwords will die. We have been told that passwords are dead for many years, that multi-factor, passwordless, everything else will replace them and they will disappear forever. The reality is that 90% of the authentication events today use a password. Whether we like this or not, it's completely irrelevant, but as security specialists, we want to make sure that what is happening is secure while we wait for the future, where that distant future where passwords will finally die. So why do we want to know more about passwords, and why do we want to know more about passwords in the particular field of mainframe security? As we've seen, and as all statistics tell us, passwords are still the most used authentication method, especially in enterprises. Consumers may use different authentication factors, like tokens and biometrics and so on. But in enterprises, the vast majority of authentication events are based on passwords. Secondly, even if we use MFA, most often the password will be one of the factors used in MFA. So we'll have a password plus something else. In case we use passwordless, passwords are most often the fallback mechanism. So in case passwordless stops working, you'll have a recovery password, a recovery key phrase, and so on. So you'll still have passwords as an authentication mechanism. For this reason, we don't want to have bad passwords. What are bad passwords? So bad passwords are either predictable passwords or weak passwords, which are not difficult enough to guess. They can be leaked passwords. That's passwords that have already been compromised and published on the internet, available to hackers to download and try them against your systems, or passwords that are shared. Shared means that we have multiple accounts using the same password. And we can also have multiple accounts using the same password on systems with different security levels or security features. We can have the same user using the one password for their email account and for the admin account, or we can have users who have the same password on Active Directory, which is a very easy to crack system as on the mainframe. So shared passwords are one issue that we don't want to have. So for security reasons, we must have good passwords. For compliance reasons, we really must have good passwords, because even if security is not that important for some of us, if we fail compliance checks, our business may be put on hold. We can be fined. Reputation goes down. So compliance is often very important. In the view of some managers, it's even more important than security. We don't agree, but they tend to. Well, why are we doing this exercise? Why are we doing this presentation? Is that the reason is that we have a solution called EPAS, which is used to detect and prevent weak, leaked, shared passwords from being used in any environment. Mainframe password support has been present in EPAS from day one, that is 2013. Support for KDFAES hashes, which will be a subject that we are going to go more in depth today, was added to EPAS in 2017. EPAS is a solution that we have now deployed in some 30 countries for thousands of servers for millions of accounts, aiming to make sure that, well, they might have many security problems, that they will never get hacked because of bad passwords. Okay, a bit on the history of passwords on the mainframe. First time there's something that is worth mentioning is 1976, when I was born. Not because of that, it's because Microsoft has introduced masked passwords on the mainframe. That's basically just an obfuscation, is reversible. This would be a sad example of how to store passwords by today's standards, because there is no cryptographic effort involved. But it was quite interesting for that time. It was quite original and signaled a shift to something that says that we should not really show our passwords around if we get compromised, even if it was quite easy to decrypt them or to decode them. Fast forward to 1984. This is when we've seen for the first time DES encrypted passwords. This is real password encryption. It is actually salted password encryption, where the username is used and encrypted with the actual password. This mechanism, although it was implemented in 1984, respects the basic requirements of a secure password even by today's standards, meaning that we have a one-way encryption. So from the hash, we cannot get back the password directly. We have to try to crack it. And it's also salted, meaning that two users having the same password will not have the same hash. So we cannot use this information in order to crack hashes. To put this into perspective, even today, Windows systems, Active Directory, uses NTLM hashes, which are still not salted. So two users having the same password will have the same hash. Looking forward to 1994, DES encrypted passwords became the default option on mainframes, replacing masked passwords. Forward 2005, we have mixed case passwords support for mainframes along other security features. And that means that before we could only use capital characters and a few symbols and numbers for our password. Now we can use also lowercase characters. Interesting enough, even today, this is not very much used, probably for compatibility reasons. Most mainframe applications still use only uppercase passwords. 2006, next year, we had support for password phrase. IBM has implemented password phrase support. These are very long strings where we can write whatever we want, and we can use all kinds of characters, uppercase, lowercase, and so on. They are not replacing passwords. They work in parallel with passwords, because we still needed passwords for compatibility reasons. Password phrases are offered by IBM as an alternative to passwords, a more secure alternative. Not very lucky, though. The password phrase encryption mechanism is pretty much broken. That means that we can have multiple different passwords yielding the same hash. That means that in practical terms, if I have, for example, if you see at the bottom of the screen, IBM user account with the password, the good password 2001 and set, it will have the same password hash as a good password 2002. So the user can log on with either of these passwords. So in terms of cryptography, this is not good. Then 10 years later, 2014, support for KDFAES hashes appeared as an EPA. And this is when mainframe passwords really received a modern password hashing algorithm. That means very hard to crack, very slow to be computed, comparable with modern operating systems like, I don't know, macOS and Linux and so on. So it went in the same league and even exceeded it with this new implementation. IBM decided for their own reasons to keep the algorithm secret. We don't really agree with that, but it was their choice. Many companies do that. However, 1 year later, 2015, the KDFAES algorithm has been discovered independently by at least 2 researchers, one from us and one from IBM-Z software, independently. And then in 2017, KDFAES has been implemented with full GPU hardware acceleration support in Hashcat. We did that for our EPAS solution in order to be able to audit mainframe passwords and help our customers with password security. Just a few technical details, sorry if it's too technical, on the KDFAES algorithm. In the first step, we have an input for the key derivation function. And so for passwords, the old DES password hash is used as an input function. This is quite intelligent, actually, because it permits one-way migration of all DES passwords to KDFAES. So we get the advantage of a stronger password hashing without having to wait for all the users to change their passwords. It also allows us to do a massive migration of passwords to say, okay, from today, all my users will use the new encryption algorithm, and it happens. There is no wait in between. For password phrases, this is not valid. So for the password phrases, we have a new input for key derivation mechanism. We don't know why. Maybe it's because the previous algorithm was broken, but migration is not possible. So password phrases will benefit from the new algorithm only after the password phrase is changed by the user. In step 2, we have the actual time-consuming step, where which makes the algorithm strong. So this is the step that will hinder attacks. It will make attacks unfeasible. This is based on an IBM customized version of PBKDF2 with SAJ256 with 45,000 rounds. The actual algorithm is changed. It's not the standard one. It has minor changes, very hard to understand. But this also means that if you have any kind of ASICs lying around for cryptocurrency mining or I don't know what, you cannot use them to crack mainframe passwords because they will not fit. You will need specially designed hardware for that. In step 3, we use the output from the key derivation mechanism to encrypt the username with AES-256, and together with the random salt, this is the information that is stored in the RACF database. Unexpected benefit, in case you're worried about quantum computing attacks. Both functions use SSJ256 and AES-256 are believed to be quantum safe, so quantum computing attacks would not be able to increase the speed for cracking these password hashes. The algorithm also includes in its formatting 2 parameters. One is called the memory factor and the second is the repetition factor. These factors can be customized in order to increase the complexity, so to increase the required resources and the time taken to calculate the hash. In case computers get much faster in the future, these parameters can be tuned in order to make password attacks unfeasible. They are not used for now, but if they will be maxed out, the computation time for a hash will increase by about 4,500 times, which is significant. At the bottom of the screen, you have a link to the actual C implementation of the KDF algorithm made by my friend Chad Rickardson from ex-IBM-Z software. If you're curious to see more details, it is open source. Now, if we want to crack passwords, if we want to crack KDFAES passwords, so what will be your attacker doing? What are the tools of trade? We have, starting from the top left corner, clusters. We have individual computers, each of them using a high-performance GPU, where we have an optimized cryptographic implementation of the KDFAES algorithm. Every computer in the cluster will have one GPU, and they are configured to work together in order to split the workload between them. At the bottom, we have an alternative implementation, which is a computer with multiple GPUs. In this case, it's a 10 GPU worker module, what we call it. So it's a single computer with 10 GPUs. That also can be configured to work in a cluster, so multiple computers of this size. These are normally not used for normal password audits. We provide this kind of hardware primarily to law enforcement, where password recovery is essential for their ongoing investigations. Normal companies would use for password auditing a single computer from the cluster on the left-hand side. The other option available, not only to professionals, but also to attackers, would be to use virtualized hardware. Amazon and other cloud providers have virtual GPU instances of 8 GPUs, which provide very good performance. Okay, the price per hour of use is quite high, but the initial investment is close to zero. So if someone really needs to crack some passwords and they want to have a high-performance solution and they want to throw a few $100s at it, Amazon or Azure would be their best option. So how do we use these tools, and how can we use them in order to understand what would be the benefits of the new mainframe password encryption algorithm of KDFAES versus the old one? What are the weaknesses that are still left or not, and what can we do to protect ourselves? In order to understand, we will start with DES. Yeah? So what we had before KDFAES was DES, and we'll look a little bit at the performance. I'm using our EPAS solution for the performance ratios and for the examples. Also, it's for marketing, naturally. So in this example, we have an attack against a DES encrypted password. We have a brute force attack, so basically trying all the possible combinations in order to crack the password. We have one user, and we really want to get the password of this user. We can see in the green box that the performance ratio is about 8 billion hashes per second, so it's quite fast. We have a guaranteed recovery of any password in up to 13 minutes, and this is on a 1 GPU unit alone. Yeah, if we have 10 GPUs, of course, it's 10 times faster. So just to set the benchmark, one user will have the password 100% sure cracked in 13 minutes with the old password encryption, with DES encryption. If we compare this to KDFAES, exactly the same use case, the same password that has been migrated to KDFAES. We have guaranteed recovery based on the speed. So instead of 8 billion, now we have only 72,000 hashes per second. That means that it will take us to crack the same password 858 days. This is quite an improvement. Started with 13 minutes. And this is for GPU accelerated cracking. If you look at the bottom of the screen, this is an example for no GPU acceleration, so just using a computer without any specialized hardware. This will be 70 times slower. So first question would be, how much better is it with KDFAES over DES? If we look at brute force attacks, well, much better, from 13 minutes to 858 days. We'll look at the numbers a bit later. Let's look at another type of attacks. This is actually the most popular one. Nobody tries passwords with brute force these days. Nobody tries all possible combinations. It will take forever. What attackers would do, what specialists would do, is to maximize their chances of cracking a password by using a word list, so a prepared list of words that would be used to match the password. They will try those and not just random combinations. They want to find passwords which are in that word list or similar to that word list. And that word list can be words from a language. That can be collected password leaks, which are actually the best, or any custom dictionary that is made based on information on the target. Yeah, so public image of the company, data from the website, data about the employees. Everything can be used to build customized word lists, which yield very good results when it comes to cracking passwords. Looking at our example here, we have a 35 million entries dictionary, 100 users, DES encryption, as in the first example, and we want to see how quickly can we go through all the possible combinations for these users. With DES encryption, it takes us 5 seconds. Let's see how long it takes for KDFAES. For KDFAES, same example, going through all the possible combinations for 100 users takes us 6 hours. So it's 3 seconds versus 6 hours. So good point for KDFAES. Now, let's do a brief summary to see what this means in numbers. Yeah. How much better is if we use KDFAES instead of DES? Or how much harder is it for the attacker to crack your password today if you are switching to the new algorithm? The top half of the screen, we have the basic numbers compared, the actual numbers compared. In red, we can see what is on the 1 GPU, 10 GPUs, on Amazon virtual GPU instance. Apparently, it is 85 times harder to crack KDFAES than DES via brute force attacks. Put this into perspective, this is 1.5 million times harder than NTLM, which is used by Active Directory and Windows in general. This comparison is not really the best because, yes, algorithms have improved, but also we get more performant hardware today. So the question is, compared to when DES was mainly used, let's say 2010, to when KDF is mainly used, which is 2020, how harder is it to crack hashes if we invest the same amount of money? Let's say we take 3,000 euro. If we take the same amount of money and we spend it on hardware, compared to what we could do in 2010 and what we can do in 2020, it appears that it is somewhere between 11 times harder and 2,500 times harder to crack a RACF password today than it was 10 years ago. This is, of course, because while IBM has implemented a better algorithm, we also have access to better hardware for the same amount of money. So, based on these examples, can we say that RACF passwords are now safe or not? Well, brute force attacks are no longer a viable option. That's really not going to fly. It takes too long. But still, if we use OpenCL acceleration, so GPU acceleration, and up-to-date GPUs, so later generation of GPUs from NVIDIA or AMD or cloud resources, we can still have a good speed, somewhere between 80,000 and 800,000 hashes per second, which makes password attacks viable. However, in order for these attacks to work, we have to do what is called key space streaming, meaning that we are not going to try all possible passwords, but we are going to only try those which can work on the mainframe. So in the past, I didn't care if I tried passwords of 64 characters because they were just fast enough. Today, I will only try passwords that are 8 characters long and which respect the character requirements for the mainframe I'm trying to attack, so only uppercase or mixed characters and so on. So key space streaming and preparation of the attacks is much more important than it was before. And if we look at how a real attack will happen, nobody wants to crack all the passwords. Yeah, they will target important accounts or interesting accounts like service accounts, privileged accounts, developer accounts, or maybe just focus on TSO access accounts. And your typical attacker will use word lists, so lists of candidate passwords which are customized for the current target type. They will not just use all languages. They will create passwords based on what leaks they can find about your company, they will use your company branding information and everything else they can find, maybe during OSINT, social media about your employees and so on. And these word lists are very good actually in cracking passwords. Or even better, what we do, because we also have consulting services and we do mainframe pen testing, when we have to run a RACF security assessment, especially if we are doing it more like in a red team model, instead of looking at RACF databases, if we find that it uses KDFAES, we say, oh, it's going to take too long. We are targeting first a weaker system. Most often it's Active Directory. All the companies where we tested the mainframe ever, they did have some Windows domain services, some Active Directory in there. Maybe there will be companies which don't have. Maybe we haven't seen any. So we would just target Active Directory first. Grab a copy of the database with the passwords there and try to recover those passwords first. And then we will use the password that we have cracked. We will assume that most users will use the same password on the mainframe, or at least a similar password, and we'll use that thing as an input for measuring the security of the RACF password hashes. And what happens, we've seen the next two slides. So if we take an NTLM database, typical company, 10,000 users, 12-character passwords, and we run a full password audit using brute force, using dictionaries and so on. In this case, this is a real case, it's not a made-up case. We were able to recover 80% of the passwords in 2 hours. I mean, cracking 80% of the passwords in 2 hours. And if we look at the actual password composition, then we look at it. It's a typical one. In the top half, we have the entropy of the passwords, the randomness measured together with language characteristics, and at the bottom part, we have the length of the passwords. So we see that we have a very typical distribution of how passwords will be composed in your average enterprise. Now we are going to use this input in order to target 100 selected accounts on our mainframe system, which have passwords encrypted by KDFAES. So in the previous step on Active Directory, we cracked 8,661 passwords, and we are going to use them in order to see if the mainframe users have the same passwords or have passwords which are only slightly different from those. Maybe they are shorter. Maybe they used a 12-character password on AD and they used only the first 8 characters on the mainframe and capitalized. For this, we'll use derivation rules, which simulate the way humans construct passwords from normal words when they believe they are secure, by appending a special character, putting numbers in between. Computers can do this too. The result is that in 2 minutes, we are able to recover the passwords for all our 100 users. Okay, we selected users that we knew that we'll be able to crack for this case. But it shows that if we can leverage a system which has weaker encryption first and use the output from that in order to target our mainframe, success is more or less guaranteed if it's the same company. So I have 2 minutes and 5 seconds, 100% recovery rate. This was a ZOS 2.1 system. Okay, in brief, we can still do password hash attacks against RACF. This is still possible with the new algorithm. It's not like it disappeared and we can no longer crack mainframe passwords, but it's much harder and yield less cracked passwords. And as a side comment here, it is up to the level of the other modern operating systems, as I said before. Almost specifically, we don't know any other system which has a better password hashing mechanism in place today. However, as long as weaker systems exist in your environment, well, a chain is only as strong as its weaknesses. So your attacker will target something else. They will not go for the mainframe first. Mainframe will come later, but they will go for Active Directory, they will go for Linux, insecure Linux machines, web services, application servers, operator consoles which run Windows and are enrolled in the domain. Those are very attractive targets. They will use those first, get their input from there, And if passwords are involved, they are going to use the information they are getting from there in order to target your mainframe passwords. So password cracking is usually not the way mainframes are hacked, but in most of the cases instrumental. And it allows quick migration around in the environment. It opens the doors for a lot of deeper penetration. So it's very important to make sure that strong passwords are used and they are not the same passwords or they are not similar to passwords that are used to protect other systems, especially weaker ones. And this is for security, it's not for compliance. Now, one popular type of attack, and usually quite successful, is what is called password spraying. Password spraying is when your attacker will take leaked passwords, passwords that are published on the internet, compromised password databases. We select the ones that most likely fit your company because, looking at email addresses, people's names, and so on. We'll create a list, and then they will use that in order to try to authenticate to your system. That's quite a successful attack in general. So it's quite important to make sure that leaked passwords, we'll have a little bit more on that immediately, are detected if they are in use on your mainframe, and if it is, change them. Make sure that you don't use any leaked passwords. Another thing you can do, or you should do, if you have in your sysplex multiple RACF instances and you use RACF to synchronize RACF databases, always keep in mind that the password synchronization involves the transmission of the password in clear text. Okay, it's done over an encrypted channel, but the receiving RACF instance will receive it in clear text, and then it will store it in that particular database by using the encryption algorithm configured. So it's mandatory that all participating RACF instances will use KDFAES. We've seen cases where at least one of them was still using DES, and as a result, we had also DES hashes in this landscape. Even most of the other systems were using KDFAES. Talking about password leaks. Let's see how this can be used in a kind of an attack or audit, the positive way, against the mainframe. I have a database that we provide with our solution, which includes all the passwords that have what we call ever been leaked on the internet. Basically, all the passwords published on the internet between 2000 and 2021. It contains a little bit above 1 billion entries. And we're going to see if we can, and if and how, and if it's feasible to use this data against KDFAES encrypted hashes, encrypted passwords. So first of all, we are not going to try all the passwords leaked because some of them are long or use special characters which are not allowed on the mainframe. First, we are trimming this down to only those passwords which can be used for the mainframe account. In the case we are using here, we only have uppercase 8-character passwords, the most typical case for mainframes. Passwords longer than 8 characters are chopped down to 8 characters, only the first 8 characters are used. So we end up with 723 million password candidates. So these are all previously compromised passwords. And if we run the attack on EPAS, we see that with one GPU, it takes us 2.5 hours to try all these passwords for a single account. It's a long time, but it's not so long. So if I want to try it for 10 accounts, it will take me 20 hours, which is still decent. So it's a feasible attack. It's an attack that can still be used against mainframes. Okay, so this was on mainframe password theory, where we started from, where we are today, and we've seen what are the attack mechanisms, and it is still possible to target mainframe password hashes today with today's technology, although it's more expensive and it has to be done in a more technologically advanced manner. It is still a feasible attack. Let's look briefly at the end at what other authentication improvements we have seen on mainframes, and because we use our solution to audit everything related to mainframe authentication, it means also that we are looking at pass ticket seeds, for example. Previously, pass ticket seed, so the seed that is used to generate the one-time password, which is called pass ticket, that can be used as an alternative to password on mainframes, was stored in clear text in the RACF database. Okay, it was obfuscated somehow, but essentially was stored in clear text. If someone gets a copy of the RACF dataset, they can get the pass ticket seed. We use this to in both our pen tests and in our EPAS solution to see if the pass ticket seeds are truly random and unpredictable, of course. Now, one improvement that we've seen, I think 2 years ago, is the availability of HSM-backed pass ticket seed storage. That means that if someone grabs a copy of the RACF database, they will not have the clear text pass ticket seeds any longer. They are sealed to the HSM, so basically without the HSM, one cannot use the pass ticket seeds. That makes it exponentially harder to extract the seeds that are used to generate OTPs, and it makes the pass ticket method as secure as, for example, a smart card or any other thing that uses a secure element to store key material, which is excellent. Another thing that we can use to improve our authentication or to decrease the chances of an attacker to succeed when hacking our system is, of course, MFA, multi-factor authentication. There's a lot of marketing today about MFA. They say, oh, they will kill passwords and they will eliminate passwords and so on. This is not the reality, but the reality is that you can use MFA to improve your security. And if you use it for the correct use cases, then it's going to make a difference. Now for mainframes, this is nothing new. It has been refreshed marketing-wise to sound modern and fancy, but the reality is that mainframes had MFA since about 2016. Even more, RSA secure ID tokens, for example, have been supported in the mainframe for more than 20 years. And pass ticket one-time passwords have been there since something like forever. So mainframes did have MFA before the MFA term was even used. And it's a very mature and effective implementation of MFA. So if your use case supports MFA, and if your users are not going to get angry too quickly, if you force them to use MFA, give it a try at least for very sensitive accounts. Well, as I said, MFA has not killed passwords, and we don't expect it to replace passwords, but it occupies a very specific niche, says very specific cases, and it should be used for those cases. Especially when we think of administrator accounts. Of course, you cannot use it for application accounts or service accounts. You cannot instruct a server to use MFA tokens if the MFA token is a physical thing. So that's not going to fly. But you can still use MFA to improve your security. And something to keep in mind as well is that even when you use MFA, you will still have a password and often a recovery password. So make sure that that thing is secure. And yeah, to end this presentation, what we provide, what we at Detack provide, our EPAS solution, which is an enterprise password analytics solution, is something that enables you to practically measure the strength of your password security. Before that, we had password policies that we set on our systems, and then we hoped that this would prevent attacks. There was no way to measure the effectiveness of our policies. Well, we knew they were bad when we got hacked, but before that, there was not much we could do. At least in Germany, password cracking is illegal, so you cannot go around crack people's passwords and then tell them it's bad. Your password is bad, you can't change it. It's private information. With EPAS, we don't have this problem because we run in a sealed environment. We never store, we never display passwords, and it's very well approved in environments where privacy matters. So with EPAS, we can measure the quality of the existing passwords. We can detect if the existing passwords have been compromised or are shared by multiple users. And with what we call the EPAS enforcer, we can prevent this password from being used. That means that, for example, following NIST recommendations or other compliance requirements is really a piece of cake. And that's it. Look at questions. Patrick, you're mute.
Yes. Thank you very much. So thanks a lot for the very interesting intro and overview of passwords and your Detack solutions. So before I go to the world out there, I have a very personal question from my side. So you talked a lot about passwords and mainframe and things like that. So compared to other platforms, what makes it special or unique for passwords on mainframe compared to other platforms?
Well, I think that's one thing is that the maturity of the password. So let's say you are only using password. You're not using any kind of multiple factors and so on. The security of the passwords on the mainframe and the way the password hashes are stored, this makes it much more difficult to recover the passwords, to correct those passwords as compared to other systems, in particular Microsoft, because this is what you find in most places. You see Microsoft systems. So that's one thing. So KDFAES really advanced this to a new level. Then if we look at one-time passwords, for example, pass tickets, this is natively supported on the mainframe. It's very mature again, and as of about 2 years ago, it has a secure element of hardware security module support, which means that without any third-party product, you can have a step-in replacement for your passwords. You have one-time tokens instead of passwords with zero effort. I don't know of any similar functionality on other systems. You can even configure RACF to be an LDAP server and allow other systems to use this kind of authentication for themselves, which is an even better thing. And the last thing, if we look at MFA or passwordless methods, like certificates and so on, this is again something which is natively supported and very mature on the mainframe. Many other systems use some kind of patchwork, what is called enterprise single sign-on, which is just another way of saying I have a password manager that will type the password on my behalf. This is quite primitive compared to what we can use on the mainframe with the existing functionality. So, and again, we can use the mainframe as an authentication backend for other systems which are less secure. So we can do both things. That's in my opinion. This is how I see a comparison between mainframe and other systems. I like
great.
it.
Great, thank you very much. So, very interesting piece in the whole story of our ecosystem series. That the password, and as you said, securing from a mainframe in the back, even to other systems, and passwords are still there, even if I have my smartphone in front of my face, and passwords are still there. And thanks a lot for giving us a glimpse into what the meaning of a password, the importance of password is in today's world, and in the overall IT, so to say. Let me have a look. I don't think there are any special questions, but we have a nice comment for you. So it was very easy to understand by how you explain it. So I'm
happy. Thank you.
So so last chance out there to post any question. 3, 2, 1. I don't see any additional questions. So once again, thank you very much, Costin and Octav. It was a pleasure to have you on stage today, talking about passwords. And for all of you out there, I'm really looking forward for the next session and hope you will join. So thanks a lot. Have a nice day and enjoy. We will see you soon.
Thank you, Patrick. Thanks, everybody.